Academy. In this video, we are going to discuss about Galois theory. That is, we are going to see how to find the Galois group for a given polynomial. First, let's see what is meant by a fixed field. Throughout this video, F denotes a given field and K denotes the extension field. Already I have uploaded on video for extension field. So if you want to know the basics, you go through that video. So here F is a field and K is an extension of F. Here G denotes group of automorphisms of K. Right? What do you mean by automorphism? It is isomorphism of a field into itself is called what? Automorphism. So G denotes the group of all automorphisms of the field K. Then what do you mean by fixed field of G? See, fixed field means the set of all elements of the field K for which sigma of A equal to A for all sigma belong to G. See, we are taking sigma denotes an automorphism. Okay, sigma denotes an automorphism of K onto itself, right? So whatever automorphism you take, for all the automorphisms, the elements are fixed, sigma of A equal to A. Then the collection of all the elements A denote what? Fixed field of G. Okay, right. Next one, let K be a field and F be a subfield of K. Otherwise, how can we say F is a field and K is an extension of F? Then we consider G of K comma F. This is nothing but, already I told you, G denotes the group of automorphisms on K, right? Then G of K comma F means that is nothing but the automorphisms defined on K which fix every element of F. Okay, that is G denotes the automorphisms on the field K and G of K comma F denotes what? The set of all automorphisms defined on K which leave every element of F fixed. Okay, that is sigma, an automorphism belong to G of K comma F if and only if sigma of alpha equal to alpha for every alpha belongs to F. Okay, so this is a what? This is a subgroup of G of K comma F is a subgroup of group of all automorphisms of K, right? Every rational number is left fixed by every automorphism of K. Suppose if K is any field containing the field of rational numbers, then every rational number will be fixed by every automorphism of K. This is a property which we frequently use for doing problems. Okay, because for all the polynomials we used to take only rational coefficients, no? So this concept will be used in all the problems that we are doing in this video. Next one, if K is a finite extension of F, then G of Kf, what about the number of elements or number of automorphisms in G of K comma F? Order of G of K comma F is less than or equal to degree of K over F. What do you mean by this? See, F is a field and K is an extension field. This is called degree of K over F. That is nothing but dimension of K as a vector space over the field F. All these things I have explained in the previous video. I have given the link for the playlist in the description. Okay, so if you want to know the preliminaries, you go through all the videos. Right. Next one is K is a normal extension of F if K is a finite extension such that the fixed field of G of K comma F is F. So normal extension, we know what is an extension. Okay, and we know what is a finite extension. When will you say an extension is finite? When the degree of K over F is finite, it is called as finite extension. So for an extension to be a normal extension, first of all it has to be a finite extension, and then the fixed field of G of K comma F must be equal to F. That means the set of all automorphisms in K which fix every element of F is F, no, that is entirely equal to F. Otherwise, K is a normal extension of F if and only if K is the splitting field for some polynomial over F. This K should be splitting field for some polynomial, any polynomial of F. So for example, see, Q root 2 is a normal extension of Q. Because, see, this is a polynomial, no, x square minus 2 equal to 0. This is a polynomial with rational coefficients. This is irreducible over Q, that we know. Why it is irreducible? Because root 2 is the plus or minus root 2 or the roots of this polynomial which are not there in Q. Therefore, what is the splitting field for this polynomial? Q root 2. So Q root 2 is the splitting field. Therefore, what can we say? Q root 2 is a normal extension. Because for a field to be a normal extension, what we say here? It has to be splitting field for some polynomial over f. So here Q root 2 is the splitting field for this polynomial. So what do we say? Q root 2 is a normal extension. Okay, right? Then next one is, here we are defining what is a Galois group. Let f of x be a polynomial in capital F of x and k be its splitting field over f. That means we have a polynomial defined over the field f and this is irreducible over f. So it is irreducible over f means we have to find its splitting field, no? Okay, and that splitting field, that extension field, we call it as k. Then the Galois group of f of x is the group g of k comma f. What is the Galois group? Galois group of f of x is nothing but g of k comma f. That is the set of all automorphisms of k which leave every element of f fixed. Okay, so the Galois group means it is nothing but the group of automorphisms of the splitting field which leave every element of f fixed. So this is called the Galois group for the given polynomial, right? So Galois group means that is we define for a polynomial and the Galois group contains what? What are the elements of a Galois group? They are all automorphisms. Okay, the elements of the Galois group are automorphisms. So in Galois theory, actually what we are doing is we are finding the relation between a field and a group. Okay, so this group of automorphism we are connecting it with a splitting field. Okay, so we are bringing a connection between a splitting field and Galois group. That is a nice relationship between a group and a field. Okay, next one. Let k be the splitting field for f of x in capital F of x and let p of x be an irreducible factor. See, I am taking one field and a polynomial over the field. Okay, so this polynomial is not reducible over f. That means it has some irreducible factor, no? That irreducible factor I am taking it as p of x. Suppose the roots of this p of x are given by alpha 1, alpha 2, etc. alpha r. Okay, then we can find for each of this root, we can find an automorphism in the Galois group such that sigma I of alpha j equal to alpha I. This is nothing but we are bringing a permutation group, okay, permutation group in the what? In the group of automorphisms, right? Okay, next one is fundamental theorem of Galois theory. This theorem says if f of x is a polynomial in capital F of x and k is its splitting field over f and g of k comma f is the Galois group. So these are the notations we are using. F is the polynomial, k is its splitting field and g of kf is the Galois group. Then for any subfield t of k which contains f, g of k comma t. So g of k comma t denotes what? The set of all automorphisms in k which leave every element of t fixed, right? And for any subgroup h of g of k comma f, kh is defined to be set of all x in k for which sigma of x is equal to x for every sigma belongs to h. Then there exists a one-to-one correspondence of the set of subfields of k which contain f onto the set of subgroups of g of k comma f. Okay, we create a one-to-one correspondence between the subfields of k and the subgroups of g of k comma f. So what are the things that are satisfied? T equal to k g of k comma t and h equal to g of k comma kh and index of k over t equal to what is this? What do we say? Degree of k over t is equal to order of g of k comma t and t is a normal extension of f if and only if g of k comma t is a normal subgroup of g of kf. When t is a normal extension, g of tf is isomorphic to g of kf by g of kt. Okay, right. Let us see some examples First one, let us consider the simplest polynomial x square minus 2 equal to 0. So this is a polynomial over the field of rational numbers. Because the coefficients are rational numbers, no, so this is considered as a polynomial over q. Now you see x square equal to 2, so x equal to plus or minus root 2. So this given polynomial is reducible over q of root 2. So how to find the splitting field for a given polynomial also I have uploaded in a separate video. Okay, so q root 2 is the splitting field. Okay, let me take q as f and the extension q root 2 as k. Okay, just for convenience I am taking. So when the polynomial is given, first you find out the splitting field for the given polynomial. Okay, now next let sigma be an automorphism over k. I am taking one automorphism over k. I am going to find what is the fixed field for g of k comma f. So if sigma is an automorphism, what is sigma of root 2 square? Equal to sigma of 2. Because see, plus root 2 and minus root 2 are roots of this equation, no? So root 2 square equal to 2 and minus root 2 square equal to 2. So sigma of root 2 square equal to sigma of root 2 square value is what? 2. So it is equal to sigma of 2. See, sigma is an automorphism, and I already told you that every rational number is left fixed by every automorphism. So 2 is a rational number, no? So sigma of root 2, sigma of any rational number is equal to the rational number itself. Okay, this property I have stated already in the beginning of this video itself. So sigma root 2 square equal to 2. That means if you take square root, what will happen? Sigma of root 2 equal to, if you take square root, what will happen? Plus or minus root 2. That means if sigma is any automorphism, then how it will act on the roots? Okay, sigma of root 2 will become either plus root 2 or minus root 2. Let me take these two as different automorphisms. So these two are the only two automorphisms which are existing there. Let me take sigma 1 of root 2 equal to plus root 2 and sigma 2 of root 2 as minus root 2. So this is nothing but your identity map, and this let me take it as sigma. Therefore, what are the automorphisms? E comma identity E comma sigma. Right? Now, how will you take any element of q of root 2? See, q of root 2, every element takes the form a plus b root 2, where a and b are elements of q. Right? So, what will happen to this element under these two automorphisms? See, E, identity map of E plus b root 2 is equal to a plus b root 2 only, because this is identity map, no? So, which fixes every element. What about the sigma? Sigma of a plus b root 2 equal to, this sigma changes the sign of root 2. So, a plus b root 2 will be mapped to a minus b root 2. So, if you look at these two automorphisms, right, these two are the only automorphisms which leave the elements fixed. What are the elements left fixed by these two automorphisms? See, this bring the same element, but here this changes it into a minus b root 2. So to find the elements fixed by these two automorphisms, this b should be 0. Then only when this b should be 0, we will get what? Sigma of a equal to a and e of a equal to a. So what do you mean by that? This leaves only rational numbers left fixed. That means q is the fixed field. Therefore, the fixed field of g of k comma f equal to q. Okay, and what is the Galois group? Galois group equal to E comma sigma. The Galois group contains only two elements, right? And the fixed field is equal to q. So two answers we found out here. Next one, the Galois group is there, no? That is E comma sigma. This how will you write? See, E means what? Identity map, and sigma. This two automorphisms are identified by stating how it acts on the roots. What are the roots? One is plus root 2, another one is minus root 2. Under this identity map, plus root 2 goes to plus root 2 and minus root 2 goes to minus root 2. Under this sigma, plus root 2 go to minus root 2 and minus root 2 go to plus root 2. So this is nothing but identity. So 1, this is nothing but 1 goes to, if you take this as 1 and this as root 2, 1 goes to 2, 2 goes to 1. That is this permutation. So this is nothing but what? S2. Okay, so what we have concluded here, this Galois group is similar to our permutation group S2, right? This is what I have explained you in the theory. So totally what we have seen here, how to find the Galois group, how to find fixed field of the Galois group, and how to correlate it with the permutation group. I hope you understand. This is the simplest problem. Next, one more problem, let's see. See, this is another problem. X square minus 3 into x square minus 5. This is a polynomial over Q of degree 4. Isn't it? So, if you factorize these terms, what will you get? X equal to plus or minus root 3 and x equal to plus or minus root 5. So, these are the roots which have this property. Right. Now, so this polynomial is reducible over Q of root 3 comma root 5. How will you write the elements of this Q of root 3 comma root 5? A plus B root 3 plus C root 5 plus D root 3 into root 5, where A, B, C, D are rational numbers. If you want to know how I write like this, you see the videos which I have already posted, right? So the elements of this field will take this form. Now, so first step, we are finding the roots, then we are finding the splitting field. Next, let sigma be an automorphism in the extension field. Then we want to find how this sigma act on our roots. 4 roots we are having, no? Let us check how this sigma is behaving on the roots. Sigma of root 3 square equal to, why every time I am taking this as root 3 square? Here, because root 3 satisfies this factor, no? So root 3 square equal to 3. So sigma of root 3 square is equal to sigma of 3. I don't know how the sigma act on this irrational number. So I want to eliminate this irrational number. So for eliminating this irrational number, I am squaring because it is of degree 2. Okay. So sigma of root 3 square equal to sigma of 3. This is a rational number. We know every rational number is left fixed by any automorphism. So sigma of 3 is equal to 3 itself. So by taking square root on both sides, what will you get? Sigma of root 3 equal to plus or minus root 3. That means every automorphism transforms root 3 into either plus root 3 or minus root 3. In the similar way, I can conclude every automorphism sigma on root 5 acts like either it goes to plus root 5 or minus root 5. Again, sigma root 3 into root 5. The same thing. Root 3 into root 5 goes to either plus root 3 root 5 or minus root 3 root 5. Okay. So these are the what? These are the things happen when an automorphism act on a root of this polynomial. Now, so we have identified what are the what are the automorphisms. So what are the automorphisms? See, let me write this table first and then I come to the Galois group. See, first one is identity. That means root 3 goes to root 3. This you can easily write. See, there are 4 things, no? That is plus root 3, minus root 3, plus root 5, minus root 5, and then their product. See, root 3 goes to root 3, root 5 goes to root 5. This is identity. Next one, just to interchange. Root 3 goes to minus root 3, root 5 goes to root 5. So what are all the possible combination with the plus or minus root 3 and plus or minus root 5? That you write. Okay. After writing these 3, you have to come to the product. So root 3 goes to minus root 3 and root 5 goes to minus root 5. So these are the 4 automorphisms that belong to the Galois group. G of k comma equal to E alpha beta. If you are not comfortable with writing this alpha beta, just you put it as gamma. That is enough. Only 4 automorphisms are there. 4 automorphisms and degree of the polynomial equal to 4. Okay, right. Now, just for my convenience, let me take the field Q as F and the extension field Q of root 3 comma 5 as K. Now, what is the fixed field of G of k comma F? Fixed field means what? The elements are kept fixed. No change in the element. Only Q. Because, see, I have told you, no, if root 3 is there, it may be either plus root 3 or minus root 3. So, every irrational number is changed their sign. Therefore, only the rational numbers are kept fixed. Okay, right. Next one is fixed field of, see, 4 automorphisms are there, no? We can take combination. See, E comma alpha, how to find the fixed field? E fixes both the elements, but alpha fixes only root 5. So, the fixed field of E comma alpha is Q root 5. And fixed field of E comma beta, beta fixes only root 3. So, fixed field of E comma beta is Q root 3. fixed field of E comma alpha beta, or you can name it as gamma, is root 3 into root 5. Only root 3 into root 5 only it fixes. Okay, right. So these are the fixed, how to find the fixed field. Next one, we have to compare it with the permutation group. See, here this is identity permutation. So 1 I have written. The next one is 1 goes to 2, 2 goes to 1. Next one is 3 goes to 4. Next one is 1 goes to 2 and 3 goes to 4. So this is a subset of S4. Okay, because 4 roots are there, no. So we have to compare it with S4, but it is not equal to S4. It is a subset of S4. Okay. This is another polynomial, x cube minus 2 over q. This is a cubic polynomial. So if you factorize this polynomial, you will get x minus cubic root of 2 into x square plus x cubic root of 2 plus cubic root of 4 equal to 0. Therefore, x equal to cubic root of 2 is one root. The other root is obtained in this way. So the roots are cubic root of 2, another one is cubic root of 2 into minus 1 plus I root 3 by 2, and cubic root of 2 into minus 1 minus I root 3 by 2. So 3 roots we have obtained. Okay, right. Now what is the degree of q root 3 of 2 over q? 3. Next one more element is there, no? Okay, that is irreducible over q root 3 of 2, and it is reducible over q of cubic root of 2 comma I root 3. One more element I am adding. So how to find the degree of the splitting field? See, degree of q of cubic root of 2 over q is 3, and degree of q of cubic root of 2 with I root 3 over q of cubic root of 2. See, this field is obtained from this field by adjoining cubic root of 2. What is the basis? 1 cubic root of 2 and cubic root of 4. So this is of degree 3. Next one, this field is obtained from this field by adjoining I root 3. So what is the degree? 1 comma I root 3 is the basis, therefore degree equal to 2. So totally the splitting field is q of cubic root of 2 comma I root 3, and degree of this field over q is equal to 2 into 3 equal to what? 6. Okay, so this is the degree of the splitting field. So this is the splitting field, and all its elements of the take the form a plus b cubic root of 2 plus c cubic root of 4 plus d I root 3. Next we have to see how does the automorphism behave on this field. Let sigma be an automorphism, then sigma of cubic root of 2 equal to cubic root of 2. So this element is left fixed. Next, similarly cubic root of 4. Cubic root of 4 is equal to cubic root of 4. So this is also left fixed. Next, what about I root 3? The sigma I root 3 is equal to plus or minus I root 3. So from this we conclude 3 roots are there, no? One is containing cubic root of 2, that is left fixed. The another one is cubic root of 4, that is also left fixed. The another one is I root 3, it is either mapped to I root 3 or minus I root 3. Okay. So from this what do we conclude? Under any automorphism sigma, the elements of the splitting field are fixed only up to the what? Up to the field q of cubic root of 2, because the imaginary part is kept unchanged one time and then it is inversed, that is it is conjugated in the other time. So the fixed field is equal to what? Q of cubic root of 2, and the automorphisms are given by, see, there are how many roots are there? How many roots are there? Cubic polynomial, 3 roots are there, no? So among the 3 roots, the first 2 roots, that is cubic root of 2, the another one is what? I have taken it as omega 1, omega 2, omega 3. So what are all the different possible combinations are there? That you have to write here, and that exactly maps with our S3, that is permutation group on 3 symbols. That is here with all plus sign we can take one value, and then with one negative sign we can take one value. No, in that way you have to rewrite the values. So this is isomorphic to what? The permutation group on 3 symbols. Okay, I hope you understand this video. Thank you.